Hi, I'm Anurag, and I'll be talking about how we use AI and machine learning to help accelerate research and development in quantum. Fair warning, this is all classical machine learning work that I'll be talking about today, so no quantum machine learning. This is all pure classical machine learning techniques with the goal of using that to improve quantum computing and quantum sensing and other quantum technologies. Okay, so let's get started. I am from Cruise. We are a startup based in Germany, roughly around 20 to 25 people. We develop software across the stack, so superconducting qubits, Rydberg atoms, ion traps, NV centers, also quantum sensing, and even photonics and MRI. And we have, let's say, a quite diverse set of users across national labs, universities, hardware manufacturers, electronics manufacturers. So let's dive right into the first part of the talk. I want to give a very quick rundown into where we are in the AI for quantum space, so that I think you might have heard quite a bit this week about quantum for AI, so I thought it will be useful to just revise where we are with AI for quantum in 2025. This is roughly following a review that came out earlier this year. You should also check that out. But generally speaking, if we start looking at the applications of AI in the hardware domain, we see mostly four different application verticals. One is in architecture search. So when you're trying to do specific algorithms, you often need to come up with optimal architectures of the circuit, architectures of the hardware that are efficient. And a lot of this has to do with the performance limitations arising from NISQ devices. So I think once we move towards FTQC devices, we'll see a lot less of these applications. And similarly, you also see quantum circuit compilation, which is again something that you want to take your algorithmic application and map it down to a specific circuit layout, taking care of errors, taking care of crosstalk, taking care of connectivity. These are areas where you see machine learning, classical machine learning. So again, no quantum machine learning, classical machine learning being used a lot. Similarly for quantum sensing, so a lot of the cold atom or the NV center based sensing routines, they use machine learning techniques very heavily for, let's say, pulse optimization, for analyzing the data. And this has, this whole quantum sensing domain has a very large set of applications that goes beyond just the whole GPS denied environments that you might be hearing about. It's also very widely used in mining, so underground mining exploration, and even there, the whole classical AI application for understanding the data is quite critical. And I think quantum error correction is where we see a lot of activity these days, both just coming up with new codes, coming up with new decoders, but also coming up with more efficient decoders for existing codes. So a big challenge with scaling up error correcting systems is how do you have efficient decoders once you have encoded your system with some error correcting code, how do you efficiently decode it at the kind of runtimes that we require for running applications efficiently. So if we move on to, let's say, slightly higher up in the stack, so if you're talking about when you are simulating these quantum devices, even this is something that we see a lot of applications for classical AI tools. So, just usual where you have this kind of surrogate methods. So you have a neural network that is trained on some traditional simulation tool, and the neural network acts as a very fast approximation. So it doesn't give you exact solution, it gives you approximate solutions, but sometimes these approximate solutions are good enough, and these see a lot of applications when trying to do things like DFT, for example. Similarly, there is also a lot of use cases in neural quantum systems. So these are, again, if you have heard of matrix product states or tensor networks, which are tools used to simulate quantum computers. Every time IBM announces a new result that there is quantum advantage, quantum utility, there will be some theory group from somewhere who will come up with some tensor network method. So this is an extension of that, where you have these neural quantum states, which are supposed to be even more powerful at simulating large entangled systems. And then, like I was saying, the whole domain of surrogate models, but also broadly digital twins, where you want to create this very accurate replica of your quantum hardware for research, for calibration purposes, for understanding the impact of error on systems, things like that. Again, very, very useful. Quickly jumping on to, let's say this is the last part of the introduction where I talk about how currently AI is being used, is analyzing quantum data. So we don't talk about this enough, but a big part of finding very good applications is how do you turn classical problems into quantum space, like how do you load them into a quantum memory, and then once you read them out, how do you efficiently analyze that data? And in this regard, we see a lot of applications of how classical AI tools can be used. So just things, very simple things like feature extraction and dimensional reduction. If you try to always use your full quantum state to get the result, it often becomes very difficult. And that's, again, where classical AI tools help. We have seen this also for error mitigation when trying to understand how to efficiently mitigate different kinds of errors that we see in quantum systems. And also for just fully understanding. So tomography is the technique of understanding what is going on with your quantum device. And again, here we see a lot of applications of classical AI techniques. So automated calibration and control is what I'll be talking about a lot today in my talk about where we see AI for quantum going in the future. There has already been quite a bit of work in the last 4 or 5 years. So everything that I presented in all the slides before, they're all from the last half decade. So very recent work. So this is still a field that's very much in the development phase. We see this kind of work where you have neural networks, almost always neural networks coupled with some traditional machine learning technique or reinforcement learning, and then applied that to pulse optimization or to characterize the system efficiently. These are very, let's say, well-established applications at this point. We see this for superconducting systems. We see this for spin qubits. Very fantastic work that really pushes the limits of how fast and how efficiently you can characterize system. So the overwhelming theme in all of the examples that I presented from the last 4 or 5 years is that they make a very heavy use of neural networks. And I think that's also something that we have largely seen in the general AI domain. But as some of you might be aware, neural networks have a problem of explainability. They're black box systems, which means that when you use them in applications such as this, where you are trying to understand your physical device, you often run into the challenge that even though the neural network might be able to give you very good answers, those answers don't go back to explain why you are getting very good answers. So that's the next part I want to talk about, that why do we need more AI for quantum, where the AI is physics-based AI and not just black box neural networks. So maybe one, let's say, hot take, or maybe it's not so hot take, is that whatever quantum computing hardware you have today, these are all engineering prototypes. We don't have devices that are commercially useful. We don't have devices that actually provide commercial value, which means everything that we're manufacturing today, it is essentially a device that should help us design next generation devices, right? So these are all devices that we make today to guide our manufacturing, our design of the next generation devices, which means that even though you might be able to use these AI tools to get good enough performance out of the current device, you might be able to get very good fidelities, you might be able to get very good applications. That's not enough because, like I said, they don't explain the behavior of the device, they don't explain the physics of the device. Because really what most hardware groups, most hardware companies, most hardware labs are doing today is that they are doing this R&D cycle. They make some generation of quantum computing, quantum sensing hardware, characterize it, understand its limitations, and go back to the lab to make the next generation. In between, they have to make an announcement in the press that, hey, we made this, hey, this is great, and that's always useful for the investors and the general public. But really, if you go back to the hardware team, what they really care about is how do I make the next generation device and how do I make it much better. So in this regard, what you really care about than just getting very good performance out of current generation devices is that you want to understand what is holding back the limit, or what are the limitations of your current generation device. So you care less about how to get the most out of your present device and more about understanding what is holding back performance so you can improve that in the next generation device. So if we look at a very concrete example of why black box machine learning, like the examples that I showed before, are not, let's say, applicable, not, let's say, useful in these cases, is that if you take the example of calibrating quantum computers, right? The usual process is that you will run some experiments on that device that will give you back some data. You have that data, you fit it to some simplified model. Usually you will fit some sinusoid, some exponential, and then you repeat this for all the different parameters. So you want to design a gate, you want to design some pulse, you repeat this for all the parameters. And usually at this point, even after all this characterization, if you're looking at something, let's say straightforward like a gate, like a 2-qubit gate, that will still be quite bad. The fidelities will still be quite low. And usually the way we address this with AI, and again, this is work that has been done in the last 4 or 5 years, is that you will take some reinforcement learning tool. The reinforcement learning tool will go ahead and will optimize the pulses in this case so that you can design better gates. And then at that point, you hopefully have really good 2-qubit gates that you can talk about in the press and everybody is happy. The problem with this approach is that you don't really get to understand what led to that improvement. Because the fact that you needed to use the reinforcement learning model means that you didn't have a very good understanding of your device to start with. But now that you have good pulses, you still don't understand what you needed to improve in order to fix your initial understanding, which is why you need a model that explains your behavior and not just gives you good performance. So this is, let's say, what I want to talk about in the next part, that how do we look at this problem of using white box physics-based machine learning. And the way we do it is with digital twins, and these are differentiable digital twins. For those of you coming from a machine learning background, that might be a well-established term that you need differentiable twins to understand systems. I'll maybe take a few seconds later on to explain how we do that. So the way we do that is with our product called CruiseML. It's a platform for modeling, learning, and creating predictive error models for quantum computers, quantum sensors. Let's look at what it really does under the hood. So when you are developing simulations for your devices, there are two broad approaches. You can either create these very first principles models where you write down the differential equations and then you put it into a solver and the solver will give you the output of the system. Or you take a neural network and then you ask the neural network to essentially learn input outputs. That if I put this input into the system, this is the output I get. I have a lot of data. Tell me, come up with a pattern recognition for this. So you have these two approaches. They are slightly contrasting in the sense that the first approach is great for explainability, but it cannot learn from data, whereas the second approach, it can learn from data, but it's completely black box, so you don't understand anything about the behavior of the system. What we have done is essentially to make these two things marry each other so that you can have digital twins which are completely physics-based, but at the same time, they provide you the learning power that neural networks have. So now you have a digital twin which has the full explainability of your physics-based models, and at the same time, you can feed it data, and that data can tell you how your system is behaving based on real behavior and not just, let's say, some theorists' ideas. So what do we need for accelerating quantum R&D? We want a very accurate, explainable, and learnable digital twin. So we don't just want a digital twin, we want a digital twin that has these three properties. And so you want it to be differentiable because differentiability is what helps you learn models from data. If you want to talk about differentiability, I'll be very happy to chat about it after the talk. But you want a differentiable digital twin which can learn from data. You want it to accurately model not just the chip, but the whole control stack, because anybody who's worked in a lab will know that a significant bottleneck in current quantum computing devices and quantum sensing devices is the errors coming out of the control stack. So it's very important to also model the control stack. And then, of course, you also want to be able to learn from arbitrary experimental data and use that to improve the performance of your digital twin. So how do we actually learn? So we start with this differentiable digital twin. Like I said, this is not a neural network, so it's a completely white box model. And then this neural network free model will actually produce simulated data. You can also have the same data coming from experiments. And once you have this, you basically have a digital twin that can learn, and you have a data set from which you can learn that digital twin. Combining these two things gives you the traditional machine learning algorithm. You can use stochastic gradient descent, any of these machine learning tools, and you essentially come out with a digital twin that is significantly more accurate in predicting the dynamics of your system. It's not just a theoretical model, it's a model that knows exactly what is happening in the hardware. So what I want you to take away from this is that you want to be able to learn arbitrarily complex physics models from data, and that is what a differentiable digital twin and machine learning algorithms let you do. So let's look at an application for this. So we are looking at superconducting qubits, very traditional setup. A common example is that if you try to do 2-qubit gates, you get this very nice plot that your theorist friend will tell you this is what the experiment looks like. But usually when you go to the lab, the experiment looks like the second picture, which is this really ugly, distorted plot. And this is, again, the gap between simulation and what you see in reality. The good thing is that because you have a digital twin that can learn from data, the third plot is again a simulation, but this time it's a simulation from our digital twin which learns from data. And you can see how clearly it represents what you see in reality. The good thing is that because this digital twin can learn from data, it can actually also tell you how to fix your experiments, and that's exactly what the digital twin has done in this case. The final plot is actually, again, plot from the experiment. So you see we went from this really ugly thing on the second one to the very nice plot on the complete right one, and in the process, we improved the 2-qubit gates by 50%. So that's a significant improvement that was only possible because you use digital twins that explain the behavior of the system. So now, where do you go from this? This is my last slide. I want to summarize how do you use these differentiable digital twins. Essentially, you have a completely physics explainable model of the system. So now you can probe this model to do all kinds of what-if situations. What happens if I stack 20 chips together? What happens if I reduce the crosstalk to 0? Does it actually have any impact? What happens if I increase my qubits decoherence time to very high values? You can do all this kind of what-if modelings. And everything in simulation. You don't need to do that on the hardware because your simulation is so very accurate and exactly represents what you see in the hardware. And this lets you, understand how to improve your device's performance, which factor has how much impact. Because at the end of the day, you want a breakdown like that. That if my 2-qubit gate is currently at 99, where is that 1% gone? Is that 1% because I have bad PhD students who don't know how to run experiments? Or is it because I have a really bad clean room and I need to get better at fabricating chips? So this breakdown is really what you care about, and that's what a digital twin like this lets you do. OK, and that's all. I don't know if you have time for questions, but if you don't, you can also reach out any of these points. Yeah.